Welcome to Chapter 6, where we delve into the fascinating world of graphs and hashing. These concepts are fundamental in computer science and have a wide range of applications. A graph is essentially a collection of vertices connected by edges. Unlike a tree, a graph can have complex relationships among its nodes, making it a versatile structure for various applications. Graphs can be represented as ordered sets of vertices and edges. For example, a graph with 5 vertices and 6 edges can be visualized as shown, illustrating the connections between nodes. To understand graphs better, we need to familiarize ourselves with key terms like nodes, edges, adjacent nodes, and the degree of a node. These terms help us describe the structure and properties of a graph. Graphs can be either directed or undirected. In undirected graphs, edges don't have a direction, allowing traversal in both ways between vertices. This flexibility is depicted in the example shown. In directed graphs, edges have a specific direction, forming ordered pairs. This means traversal is only possible in the direction of the edge, as illustrated in the example. Graphs have various properties such as predecessors, successors, in-degree, and out-degree. These properties help us understand the relationships and connectivity within the graph. In-degree and out-degree are important metrics in graph theory. They indicate the number of edges coming into and going out from a vertex, respectively, as shown in the table. A path in a graph is a sequence of nodes that leads from one node to another. Paths can be simple, closed, or cyclic, each with unique characteristics and applications. A connected graph ensures that there is a path between every pair of vertices. This connectivity is crucial for many applications, as it ensures no node is isolated. Complete graphs have edges connecting every pair of nodes, while weighted graphs assign a value to each edge, representing the cost or length of traversal. The length of a graph is determined by the number of edges it contains. This metric helps us understand the complexity and connectivity of the graph. Graph representation is crucial for storing and processing graphs in computer memory. Techniques like adjacency matrices and lists help us efficiently manage graph data. An adjacency matrix is a sequential representation of a graph, showing which nodes are adjacent. This method is useful for quickly accessing connectivity information. In an undirected graph representation, a matrix shows connections between nodes without direction. This method is straightforward and useful for simple graphs. Directed graph representation uses a matrix to show connections with direction. This helps in understanding the flow and traversal paths within the graph. Undirected weighted graph representation includes weights in the matrix, indicating the cost or length of edges. This is useful for applications requiring detailed traversal information. An adjacency list is a linked representation of a graph. Each vertex points to a list of its adjacent vertices, making it efficient for storing sparse graphs.